Great, thank you very much. My name is Alexa Gordon. I'm a fourth-year grad student, a PhD candidate as long as last month ago. And today I will be telling you about my work on the host galaxies of fast radio bursts. This is done in collaboration with my advisor, Wenfei Feng, Charlie Kilpatrick, X Petraska, and many others of the F4 and Craft collaborations. Okay, so fast radio bursts, FRBs, are a new class of millisecond radio transients. So far, we have detected thousands to date. This is what an FRB looks like. This is the Lorimer burst, the very first FRB ever discovered, actually in archival data. And you see this characteristic frequency squared sweep where the higher frequency material arrives before the lower frequency, characteristic of a radio wave going through plasma. That gives you the dispersion measure, which is the integrated column density of electrons along the line of sight. So it's a brand new field, and there's a lot of open questions, such as what even causes them. There are many theories. Some of the fun ones, of course, are cosmic strings or aliens. There's literally hundreds of theories. But we think because of both the coherence and their energetics, they are some flavor of neutron stars, likely magnetars. So another fun question that we are working on is that some FRBs have been observed to repeat, and others apparently don't. We have no idea why. So in this phase space of bandwidth versus duration, there appears to be a bit of a difference in the properties of the non-repeaters and repeaters, potentially indicating there are multiple progenitors or multiple formation channels. This is still a very active area of research. Okay, so where do I come in with this? So as I've mentioned, we've detected thousands of FRBs to date, but it is only a very small portion of those have been localized to sub-arcsecond precision, and that is precisely how precise you need to be to pinpoint them to their host galaxies. So of these thousands, only about 30 to date have been localized to their host galaxies. And with that, you get all of the information of the host galaxies. More than just a few milliseconds of radio, which is not a lot to go on. There are no other electromagnetic or gravitational wave, for that matter, components to FRBs. So before we were able to have their host galaxies, it was really just the radio. So here are a couple images showing what these galaxies look like. There's quite a diversity of environments. You have these beautiful barred spiral galaxies, dwarf blobby things, and grand design spirals. So they like to show up in a lot of different types of galaxies. Another piece of evidence we have to go off of is this apparent connection to star formation. So when the FRBs show up in spiral galaxies, they tend to occur in the spiral arms, in these knots of star formation. However, when you plot their galaxies on this star formation rate versus stellar mass phase space, the star forming sequence, the galaxies fall below in sort of this green valley, which is a bit of a mystery. If they are connected with star formation, why are they not sort of typical star-forming galaxies? So in my work, I wanted to model all highly secure FRB host galaxies. So I wanted to derive their stellar population properties, such as mass, age, metallicity, dust, and so on. I wanted to also construct their star formation histories. Unfortunately, I don't have quite enough time to go into that, but I'm happy to talk about that further. And finally, to investigate any correlations between the FRB and the host properties. So this is the repeater, non-repeater question. Do they like to show up in different types of galaxies? So in my sample, I have 23 FRB host galaxies, 17 are repeaters, 6 are non-repeaters, making it the largest uniformly modeled host catalog to date as of January when I submitted this paper. So how do I do that? I use a stellar population synthesis code called Prospector. It is a Bayesian inference code. So what you do is you jointly fit the spectroscopy and photometry of your galaxy, do some prior assumptions. I would like to highlight that of the 22 galaxies with spectra that I fit, 8 of those come from Keck. 4 of them are newly presented, 4 are from the literature. So as of the time that this was published, about a third of all FRB host galaxies had their spectra from Keck. So it was really quite key for FRB science. Okay, so you get your photometry, spectroscopy priors, and then it gives you your stellar population properties and your spectral energy distribution. Essentially how bright your galaxy is and whatever wavelength you want to look at. So what do I find? Well, coming back to this star-forming main sequence question, here's what the sample looks like. I split it up into 3 redshift bins because there can be a bit of evolution in that phase space. Color-coded them by degree of star formation, and what I find is that uniformly modeled FRB hosts trace the star-forming main sequence. So before this Green Valley question was really a matter of systematics. So in the previous work, the background catalog that they used was derived using a different stellar population synthesis code than their host galaxies. There can be, it's very difficult to quantify the systematics between those, and essentially the star-forming main sequence was an order of magnitude higher than it should have been, making it appear that the FRB sat below that. Instead, in my work, I use a background catalog that was derived with the exact same SPS code, same assumptions and priors, and find that they actually do follow the star-forming main sequence, which makes a bit more sense. So I was interested, I'd mentioned star formation history things before. Really wanted to see, well, do the star formation histories of FRB hosts, are they similar to typical galaxies? Is there anything interesting about them? But I quickly learned that when you plot 40,000 star formation histories, you get modern art. You don't really get science. It's kind of hard to interpret that. So instead, in this figure, I'm pulling out some of the moments of the star formation histories. So the specific star formation rate and the mass-weighted age. Again, I've split them up into the 3 redshift bins and have plotted them by degree of star formation. So what you see in this figure is that most FRB hosts are star-forming, and they are not distinct from field galaxies. They sit right on top of these main loci of the cosmos field galaxies. It's interesting to note that the majority of repeaters are associated with present-day star formation, but of these 3 that are less active, 2 of the 3 are non-repeaters, so potentially that population could prefer more evolved galaxies than repeaters. Coming to the question of, do repeaters and non-repeaters prefer different types of host galaxies? Unfortunately, the answer is no. So this is still very much small statistics, only modeling 23 host galaxies, but in comparing the stellar population properties of repeaters in blue, non-repeaters in pink, the black outline is the full sample. There is no statistical significance for these distributions being different. The closest one was stellar mass, with the repeaters tending to go down to lower stellar masses, but it wasn't quite a 3 sigma detection. So the question is, well, if there is a difference, when will we start to see that? It turns out that assuming these distributions are in fact correct and representative of the true population distributions, we only need about a 2 to 3 times larger sample to start finding statistical distinctions between the host galaxies if one exists. Of course, this is assuming the current distributions are representative, of course. So continued follow-up is crucial for finding if there are any distinctions between these 2. When will we get enough hosts? This is actually a very exciting time for FRB science. There are a lot of new experiments coming on, upgrades that will go from, right now we're getting about maybe 1 or 2 hosts per month to 1 per day by the end of the year. So this will mean hundreds to thousands of new hosts in the next few years. You'll actually be getting more hosts than we know what to do with, so it's a fun time to start to think about our observing strategies. With those upgrades, we are also increasing the sensitivity of the detectors. So the majority of FRB hosts sit at about redshift 0.3, but we will start to probe out to redshift 1, some forecasts even up to redshift 5 with the square kilometer array. A interesting property of FRB is that in their dispersion measure, you just get everything along the line of sight. They're an excellent probe of the intergalactic medium, so will be great for cosmology. However, you need redshifts to fully leverage the FRBs for their use in cosmology. And it is somewhat unfortunate that the higher in redshift you go, the fainter galaxies you get. So facilities such as Keck will be really crucial in getting redshifts of these galaxies as we push out to higher redshifts. So in summary, with my work, I've found by modeling the largest sample of FRB host galaxies to date, the majority of these galaxies are star forming. They trace star formation and stellar mass in their galaxies, and this is consistent with the progenitor theory of a magnetar born in like a core collapse supernova. However, there is this growing population of less active hosts, quiescent, even one in a globular cluster, which is really interesting, that perhaps is pointing towards more delayed progenitor channels. So in this case, we will need facilities like Keck to get these really faint continua, not a lot of emission lines in that case. There's no current statistical distinction in the host galaxies of repeaters and non-repeaters, but we will start finding that with just a couple more hosts. So with that, I am out of time, so I'm happy to take any questions. Thank you.